Well, a very happy Wednesday evening to you. This is where the fun begins, the radio fun anyway. This is a ham radio class. Ham radio, that's still going on? What? Yes, it is. And we're doing great and having a lot of fun making contacts locally or around the world using radios and radio systems and stations that we've built ourselves. So if you're a tinkerer, if you want to know what's going on behind the scenes, or if you just want to meet interesting people, and some of the nicest people I've ever met are ham radio operators. So come on aboard, and you can do it just by participating here in this class, and then later we'll tell you how to find a test session where you can take a 35-question multiple choice test and get your first ham radio license. And so what we do is we work out of this book from the American Radio Relay League. This is their license manual for the technician license, which is the beginning license in the United States. This is the 5th edition of this book. That's the one you want because it's got the current question pool. All of the questions and all of the answers that you might see on your test are in the book, and they're also here in the class. And so we're gonna cover those as well. And so just come on along, appreciate you. We have a live Zoom classroom with about 16 people there this evening at the moment, and about 10 folks watching us on YouTube right now. Thank you for joining us. Thank you for trusting us in helping you get into this great hobby. It's something that I love, and the whole reason I'm doing it is just to kind of give back to a hobby that has given me so much over the years. I think I said my name is Gary. If I didn't, I'm sorry. Ham radio call sign, Whiskey 4, Echo, Echo, Yankee. And let's go ahead and get started. And if you looked into Chapter 2, which is what we're going to be talking about tonight, it may have felt something like this, jumping off a cliff. Because especially for those who haven't been involved in a math class in a very long time or looked at electronic things or whatnot, but not to worry, your feelings of angst, maybe you'll overcome them quite quickly and quite easily. So don't fret about it. I did want to, though, go into, Gary, why do we have to know all this stuff? All I want to do is talk on the radio. Well, so in the United States, there are other personal radio services. The Family Radio Service, FRS, those are those small walkie-talkies you can buy at Walmart or a bunch of different places that don't require a license. They have antennas that are fixed in place on the handy talkies. They work on UHF, ultra high frequencies. We'll talk more about that tonight. And distance is really no more than a mile, much less generally. But for car to car, when you're on a vacation or something like that, FRS, Family Radio Service, works great, and you don't need a license for that. A step up from that would be the General Mobile Radio Service, or GMRS. One of our students, Craig, mentioned that he just got his GMRS license. It's easy to do. You just fill out the application at the FCC website, pay them $35 for a 10-year license, and you're licensed to operate on the General Mobile Radio Service frequencies, which are also UHF. And in fact, they share some of the same frequencies as the Family Radio Service. One big step up, though, is that they have radio repeaters on GMRS that you can talk through to get you much greater distance. So that's another radio service without requiring a license or study, let's put it that way. You have to get the license from the FCC, but it's just a matter of filling out an application. And then, of course, there's the CB. CB is still around. It's at 27 megahertz in the high frequency bands. You used to have a license, but no longer. So for road trips or things like that, Citizens Band might be something to explore as well. But what differentiates amateur radio or ham radio? Well, we have multiple frequency bands that we can use from very low frequencies below the AM medium wave broadcast band to well up into the microwave regions. So we have a wide range of frequencies, including shortwave frequencies or high frequencies that go very, very long distances. We can do that. We have different modes available. We can talk on voice, we can use Morse code, we can send radio teletype, we can send digital data signals. We have power levels up to 1,500 watts of power. Okay. And amateur radio operators may build their own equipment. Now, not so many people do that anymore, but it is something that we have the authority to do. And the FCC says, okay, if you're going to have that authority, then we want you to know something about the basics, at least, of electronics, of radio signals, and such. And so that's what this class is all about, is to get you up to speed on some of these things that the FCC feels that you need to know about to get your amateur radio license. So tonight, we go chapter by chapter in the book that I showed you earlier, the ARRL License Manual, the 5th edition. And tonight we're going to talk about chapter 2, which is Radio and Signals Fundamentals. And it's only got 2 sections, but the first section is a doozy. Radio signals and waves. So we're going to get started on that. And a little clue, if you see blue text on any of the slides that you will see in my presentation tonight, that means that it relates to a test question. So that might help you out just a little bit to focus on the things. Oh, come back to me just for a second, Bruce. The other thing that we don't do in this class is we don't go through the chapter page by page, section by section, talk about the... No, that's boring. Also, there's way more in the book than you really need to know to pass the test. So we like to come at things from all sorts of different angles. And we feel that if you can do that, one of those may click with you where the others didn't. And what we want you to experience are what I call aha moments, where you go, ah, that's what he's talking about. Because it may sound like wah, 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 wah for me. Don't worry about it. That's normal. But it will click with you at some point in time, whether you go back and review the chapter in the book, or you might replay the video. These are being recorded on YouTube, so you can do that. And you go, ah, that's what it is. So I want you to have aha moments. Now, we are going to go and do some, a little reviewing here. Because it's probably for many of you a long time since you've been in a classroom, especially a math classroom. Now this is kind of basic, and we're not going to get hung up on it, but we want to know about whole numbers versus fractions, decimal numbering, shifting things by units of 1,000. I'll just briefly mention scientific notation, powers of 10, and then there's something called engineering notation, which is a special form of scientific notation. And then we'll be talking about plugging into the metric system. So let's go over to the blackboard if we can, Bruce, and just, so whole numbers versus fractions. That's pretty easy, I mean, okay. Oops, if I get a pen that writes, of course. All right, there's number 1. Now that's a whole number. Fractional number might be 1/2 or 1/4. And we use this kind of notation sometimes to talk about antennas. We talk about half wavelength antennas, quarter wavelength vertical antennas, that sort of thing. So whole numbers versus fractions. That's something that we use here in amateur radio. More commonly, though, we use decimal numbering. So 1.5, for example, is 1.5, or 0.25 is the same as a quarter. So just to refresh your memory, we're going to be talking about things in that way as well. here's the number 1,000. And a lot of times when we're converting, especially in the metric system, we're going to be moving the decimal point around by thousands, or moving the decimal point from here over to here. You'll see that as we're going to do some specific examples tonight, but just be thinking about that as we go along. Scientific notation and engineering notation, we're not going to do that here in the class, although you'll see it in one of my slides, but you can actually have a number that is 2.0 times 10 to the second power. That's scientific or engineering notation. This is something that we'll do in the extra class, and it's very helpful when we're looking at the small amplitudes or larger amplitudes to be able to express them as powers of 10. Again, you're not going to do that tonight, other than you'll see it on a slide, but I just want you to know about it. And then we'll be using the metric system prefixes. And let's go back over to the presentation where we'll do that next. So in amateur radio, okay, on page 2-2 in your book are the metric system prefixes, and there's a bunch of them, but really we only need to deal with 7 of them. And 3 of them are for quantities greater than the base unit, and those are, and let me turn on my laser pointer here, whoops. So if we look at the slide here, so kilo, let's start there. Kilo is a metric prefix abbreviation for 1,000. You've probably heard of kilograms or kilometers, also pronounced as kilometers. That means 1,000 meters or 1,000 grams. So kilo is the metric prefix for 1,000. Going up by a factor of 1,000 is mega. Mega is the equivalent of 1,000,000 things of a base unit. So now you've heard of mega shopping or mega this, mega, but it has a specific meaning in the metric system. So the unit of frequency is the hertz, or cycles per second as we used to call it. We'll talk about that here coming up. A megahertz, 1 megahertz, is 1,000,000 cycles per second. And you'll hear about that. And then giga is the same as a billion. 1 gigahertz is another frequency range, even up by a factor of 1,000. So these are the prefixes that we really need to know in amateur radio above whatever the base unit is. Now, for smaller quantities, things less than 1, fractions, but decimals, milli is 1/1,000th. 1/1,000th. So you've heard of milligrams, millimeters. We're going to look at those here. And I'm going to show you these things in about 3 different ways tonight. And you're going to go, Gary, I've got it. I'm sick of it, but I want it to come from different angles for different people. So milli is 1/1,000th. Micro is 1/1,000,000th. Nano is, okay, now I have to use scientific notation. It's 1 times 10 to the minus 9th. I don't know what you would call that, actually. And then pico or pico is 1 times 10 to the minus 12th. There is a name for it, but it eludes me at the moment. So these are the 7 metric prefixes that we need to know about. And, okay, I'm an American. I've been around for a long time, and America had a failed attempt back in the day to convert to the metric system. Over in Europe and in other countries, it's already been done. It's a known thing, but except for science, chemistry, physics, things like that, where it makes so much sense to use the metric system. And radio is a part of physics. So we're in a scientific endeavor, but the benefits of the metric system are really pretty enormous. this next slide is a little hard to read, but you know that in the English measurement system, where we're talking about inches, feet, miles, pounds, quarts, ounces, there's really no great consistency between units. The metric system, on the other hand, is based on the number 10. And to convert from one unit to another, you just multiply or divide by 10. It's the international system or scientific system of units, and it's used, as I mentioned, in chemistry, in physics, all scientific endeavors, astronomy, what have you. So powers of 10. And we use powers of 10 all the time. In fact, well, with the advent of plastic, maybe we don't use it so much, but you use base 10 in your wallet. Think about the cash that's in there. So, okay, I said I was going to come at this from a couple of different angles. Here's the next angle. What I want you to think about is this elusive place that I'm going to call Garyland. And in Garyland, we have a unit that is called the Gary buck. So let's come on over to what we call the calculator cam. And here we have a Gary buck. Okay, the Treasury Department's going to get me for this, but okay, this is used for educational, nonprofit use. But these are the base units. So the Gary buck is the base unit in my system, and I got a bunch of Gary bucks here, you know. So we got 1, 2, 3, 4, 5. Okay, so these are the base units of Gary bucks. But let's say I had a lot of Gary bucks. All right. Here is 1,000 Gary bucks, or we could say that it's a kilo buck. 1 kilo buck is $1,000, or 1,000 Gary bucks in this case. And so here's 2 kilo bucks, here's 3 kilo bucks, here's 4 kilo bucks, and so on. So you get the idea. The same thing happens if we go even a little bit bigger. Here's 1,000,000 Gary bucks, or a megabuck. That's 1 megabuck, 2 megabucks, and then I ran out of money. Oh, no, wait a minute. We got some more money down here. Looky, looky, looky. A gigabuck. This is 1 billion bucks, 2 billion bucks. 3 billion. So you see that you can talk about the numbers using, you know, the billion and the base unit, or you can use the prefix, a gigabuck. And likewise, you can go small as well. Think of the coins. So here's a millibuck. It's 1/1000th of a Gary buck. Here's 1/1,000,000th of a Gary buck, a microbuck. And here's 1/1,000,000th of 1/1,000,000th, or a pico buck. So that's another way to consider the metric units, the metric prefixes that we'll be talking about, and that we use all the time in ham radio. Kilo is 1/1000, mega is 1,000,000, and giga is 1 billion. Again, we work on a base unit. It could be hertz or cycles per second, or in this case, it's the Gary buck. And so we have a kilo buck, we have a mega buck, and we have a giga buck. And then going down, less than 1, we have a milli, or 1/1000th, micro, 1/1,000,000th, nano, which is 1 times 10 to the -9th, and pico, or pico, you'll hear it pronounced, is 1 times 10 to the -12th power. That's the scientific notation, which corresponds to our coins that we created here. Another way to look at the prefixes, some people find this helpful, is to turn it on its side. And so here at the 10 to the 0 power, this is the base unit. Here they're talking about grams or meters. And going up by 1,000 would be a kilogram, for example, or going up by another 1,000, a megagram. Going up by another 1,000 would be a gigagram, or if you wanted to use meters. And then going smaller, again, we are just concerned with milli, micro, nano, and pico. You will get this. All right, last example here, and we're going to talk about a meter stick. You remember the meter stick from your science class in high school? So this, whoops, let me get centered up here. This is a meter stick. It is 1 meter long. So a kilometer would be 1,000 of these laid end to end. That is a kilometer, or we sometimes say kilometer. All right? So that's going big. Now going small, if you look at the divisions here, halfway there, see it says 50? 50 centimeters. We didn't talk about centa, but that's 1/100th. And then the very little divisions, if it'll focus in, if you see the little small ones right here, those are millimeters. Those are 1/1000th of a meter. So the metric system prefixes help tell you about the quantity that you're measuring and helps you transmit that information to others accurately. So there's our little discussion about metric prefixes and conversions. We're going to do some problems coming up, but yay, we made it through. A little round of applause and pat yourself on the back. we got there. All right, now I want you to get calm. Be calm, calming. We're going to make some radio frequency waves. RF. RF is an abbreviation for radio frequency energy of any kind. Oh, notice it's in blue. That might be a clue. RF is radio frequency energy of any kind. So I said to get calm. Isn't this calming? This looks nice. This is a very quiet, still pool, and somebody has dropped a pebble right in the middle of it, and you see the waves coming out from the center. And that is very analogous to radio waves coming from an antenna. And the radio waves that we look at typically look like this. This is a sine wave. And what we're looking at here on this graph is kind of like a side view of that pond that we were looking at before, with amplitude on the vertical scale and time on the horizontal scale. And so you can see that this is an alternating wave, alternating positive, back to zero, alternating negative, back to zero, and so on and so forth. So the sine wave is important, and it's used in electronics and circuits and signals, and you'll see that all the time. Now, how often this goes positive and then negative, how often it completes one complete cycle, we say is the frequency. The frequency of that signal or that radio wave. And so lower frequency signals have the fewer complete cycles over time, whereas a medium, this has a few more, and high frequencies even more. So this is just differentiating in frequency between radio waves. And frequency is the number of complete cycles in 1 second. And conversely, the period is the number of microseconds it takes, or the number of seconds, however you define it, it takes to complete one cycle. So frequency and period are defining elements of an amplitude signal, of an alternating current signal. Again, it's varying in amplitude and time. So that's frequency. I'm going to give you a hint here about frequency here in a minute, but I want to go now to wavelength. Wavelength you may have heard of It's the distance of travel of a radio wave during that period of one complete cycle. How far does the radio wave travel for one cycle? And radio waves travel very close to the speed of light. So 300 million meters per second. Remember, we're in science here. We don't talk, it's 186,000 miles per second. We don't deal with miles, we deal with meters. So it's 300 million meters per second. That is the speed of light. And so over the period of, if this was an antenna here at the left, and we're emitting the wave, and if we measure from like points on the wave, so from the peak here to the peak here, that's one wavelength, and it's traveling away from the antenna at the speed of light. That's the radio wave travel distance. How big is that? The answer is going to be in meters. We're measuring over a certain period of time, however long it takes to complete one cycle, but how far will it travel traveling at the speed of light? The answer is in meters. And so here's a little clue that frequency is where you tune your radio. Generally on radios, the frequency is what is indicated there. Okay, that's important for us. Wavelength has to do with how big the antenna you want to build for that, they're related. We'll show you the formula here in just a second. So what I want to point out here on this slide is this right here. It is the American Radio Relay League's what we call the color chart. It's the U.S. amateur radio bands in the United States. You'll find it on page 1-23, but it's not quite so pretty. Now, if you'd like to download it, you can go to this URL up here at the top, and you can actually get PDFs of the frequency bands and print them out. Or have I got a deal for you? Let me walk over here. So they print them on glossy paper. It's not laminated, I have to say, but it's glossy paper. Here are the U.S. amateur radio bands from the very low to the very high frequency. And on the back are all of the call districts for call signs, and also all of the states in the United States for worked all states, WAS. And if you would like one of these color charts, what I would like you to do is to send me an email to w4eey@arrl.net. It's right there on the screen. w4eey@arrl.net, and say, Gary, I would like one of those color charts, and here is my mailing address. If you don't send me your mailing address, I can't mail you one. But if you do that, I would be more than happy. Hams have these in their ham shacks at their operating positions. This is something that you will refer to every day of your, what we call, ham career. So I want you to have one of these. So again, just send me an email to that email address and say, Gary, I'd like a color chart, and here is my mailing address. Now, have you mailed anything recently? The cost of stamps is amazing. So if you'd like to help to defray the costs, there are ways you can do it. If you go to my website, w4eey.com, there's a small PayPal donation link. Or here on YouTube, there's Super Thanks. If you just click on that and send me $1 or $2, that would be handy to help defray the postage costs and the costs of the charts, although we buy them in quantity from the American Radio Relay League. So really appreciate any help there. So I mentioned that the frequency is how often a sine wave repeats in 1 second. 1 megahertz means that it's going up and down 1 million times in 1 second. And we used to call that cycles per second. So 1,000 cycles per second is the same as 1 kilocycle per second, and it used to be abbreviated 1 kc. Old books on radio, you'll hear this, 1 kc up or 1 kc down. 1000 kc is the same as 1 mc, or 1 million cycles per second. Well, it all changed back in the 1970s, and I was around. I remember the change. The scientific community decided to honor Heinrich Hertz. Heinrich Hertz was a German physicist that advanced radio knowledge considerably, and so they changed cycles per second to hertz. So now we don't say 1 million cycles per second, we say 1 megahertz. Hertz is the unit for frequency. And if you look at old radios, you'll see some of the older radios still have, the KC or the MC. So you can tell this radio, which was from a Zenith Transoceanic, was before 1970. And even from Radio Shack, they had these. But here's megahertz. So this Radio Shack radio was from after 1970. When we're talking about frequency, there's a spectrum of radio frequencies, from very low frequencies to extremely high frequencies up to visible light. Did you know that light is actually radio energy that you can see? So here we have the spectrum: very low frequency, medium frequencies, high frequencies, very high frequencies, ultra high frequencies, super high frequencies, and extremely high frequencies. Okay, well, you really only need to know about high frequencies, very high frequencies, ultra high frequencies. High frequencies are between 3 and 30 megahertz. We have a lot of amateur radio bands in that area. VHF is from 30 to 300 megahertz, and VHF is from 300 megahertz to 3 gigahertz. So these three bands, and there are charts you can find which have all of the frequency allocations here in the United States, for example. Where are the cell phones slotted? Where are broadcast channels? Where are the amateur radio bands? All of these things have to be plotted out and coordinated by the FCC, which is the authority for civilian radio communications, telecommunications in the United States. But as I mentioned, we don't need to know all of this. What we need to know are these. And you heard me give out the frequencies here. It goes by threes. I don't know why they do that, but they did it. So 3 to 30 megahertz is high frequency. 30 to 300 megahertz is VHF, or very high frequency, and 300 to 3,000 megahertz, or also known as 3 gigahertz, is the ultra high frequency band. Your AM broadcast band, the original radio band where we would listen to radio stations, that's in this area, actually just below. That's the medium frequency band, let's say that. Shortwave broadcasts happen in here. The Citizens band I mentioned is 27 megahertz, so that's just below 30 megahertz, so it fits in here. VHF would be the FM broadcast band in the United States, is VHF. Used to be television channels were in the VHF area, but now they've moved them all and they're up in the UHF generally, and that's here from 300 to 3,000. So these have specific meanings, and you may be asked about that on a test as well. And again, those old radios, they actually included the frequency and the wavelength. This is an old Grundig, I think. They actually had the wavelengths marked out here, along with city names where some stations were on. And remember that the wavelength is how far a radio wave will travel going at the speed of light for one cycle. And the relationship between frequency and wavelength can be described in this pyramid. On the top is speed, on the bottom is frequency and wavelength. speed in this case refers to the speed of light. Frequency is in megahertz, and wavelength is in meters. And from this triangle, the thing is, you put your thumb, or you block out what it is you're trying to find. From this triangle, we can determine what the frequency is by putting our thumb over it, and we know that it's the speed of light divided by the wavelength in meters. Or if we want to know the wavelength, we kind of block it out, and we know it's the speed of light divided by the frequency in megahertz. And if we put the frequency in megahertz, the trick is that we can, then you just have 300 on the top. So frequency in megahertz is equal to 300 divided by the wavelength in meters. Conversely, wavelength is equal to 300 divided by the frequency in megahertz. So if we rewrite this pyramid, and this is one of those things that you might want to have on your memory dump sheet, the thing that you want to write down right away when you get into the test session, 300 over frequency in megahertz is the wavelength, or 300 divided by the wavelength in meters gives you the frequency. These are inversely proportional. As frequency goes up, wavelength goes down. Or as wavelength goes up, the frequency goes down. So this is a test question. It's not in blue, but as frequency increases, wavelength decreases. As wavelength increases, frequency decreases. Just keep that in mind. This is kind of silly, but it's a test question. How do you properly write the abbreviation megahertz? Okay, it's capital M, capital H, small z. So if you're going to write megahertz, that's how you do it. Capital M, capital H, small z. If you're going to write kilohertz, it's different. It's small k, capital H, small z. That's the proper way to write kilohertz. Small k, capital H, small z. Why is it this way? It just is. So now I'd like us to go and work on the board here some practice problems dealing with metric conversion, and then also on frequency and wavelength. So what we're going to be doing is actually not necessarily metric conversion, but unit conversion. But let's take a look, and you'll see what we're going to do. So the question is, how many milliamps is 7 amps? So let's do this one together over on the board. So the first thing, we kind of define our terms. So we remember that a milliamp, now I got that one that doesn't write again. A milliamp is 1/1000th of an amp. So that's 0.001 amp. 1,000 milliamps make up 1 amp, or 1 milliamp is 1/1000th of an amp. So the question we have is, how many milliamps, well, trying to find out milliamps, is 7 amps? Well, we know that in 1 amp, there's 1,000 milliamps. So that in 7 amps, we would have 7,000 milliamps. It's the same thing. 7 amps and 7,000 milliamps is the same quantity, just a different way to write it. All right, let's see if we got it right. Let's go for the answer. And the answer is 7,000 milliamps. All right, let's keep going. How many kilohertz is an RF signal of 3,500,000 hertz? Oh my, whoops, get my dirty t-shirt here, which is my eraser, which actually works the best. I've got an eraser down there, but it doesn't work as good. All right, let's check this again. So how many kilohertz is an RF signal of 3,500,000 hertz? So kilohertz, remember kilohertz, remember how we write it, small k, I'm going to get it wrong, large h, small z. A kilohertz is equal to 1,000 hertz. (1,000) is right here, so if we move our decimal point over 3 times, it was there, now we put it there, we can convert from hertz to kilohertz. So 3,500,000 hertz is the same as 3,500 kilohertz. Let's see if we got that right. And the answer is 3,500 kilohertz. So these types of questions are on the test, and they're discussed there in the book, but I just want you to see us doing these, and after a while it'll become almost automatic. You'll know these units, but you're seeing them for the first time, so it's kind of confusing, so don't worry about it. So, all right, how many volts are equal to 3 kilovolts? This might be kind of easy, but I'm going to go over it just for sure. So a kilovolt, 1 kilovolt is the same as 1,000 volts. And the question was, how many volts are equal to 3 kilovolts? So 3 kV would be 3,000 volts. See, 1 kilovolt is 1,000 volts. 3 kilovolts is going to be 3,000 volts. Let's see if we did it. Oh yeah, 3,000 volts. All right, here's our next one. How many volts are equal to 5 microvolts? Whoa. So we're trying to find volts, and we know we have 5 microvolts. You remember micro? That's millions. So we have 5 millionths of a volt. Can you remember how we would write that? 0.000005. Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millions. So 5 microvolts is the same as 0.000005, or you could say 5 millionths of a volt. Let's see what we do. I said 5 1/millionths of a volt, but yes, so there we go. So these kind of unit conversions are things that technicians would do every day. So what is the equivalent of 1,000 millivolts? So to remember how many, what is a millivolt? A millivolt is 1/1000th of a volt. So we're asking for what is the equivalent of 1,000 millivolts? We know that a millivolt is 1,000th, and that's a factor of 3. We can move the decimal point over 3 places. This is one way to do it. And so 1 volt is the same as 1,000 millivolts. I know it might be a little confusing, but I want you to be, experiencing this. All right, here we go. We'll see if we got it. Yeah. 1,000 millivolts is the same as 1 volt. Okay, here we're going to measure some current. An ammeter measures 5,000 milliamperes. How many amps is that? Well, again, here we use millivolts, but it's the same. The base unit is changing from volts to amps. But we say that we have 5,000 milliamps. But we want to know amps. Well, milli is a factor of 1,000. That means moving the decimal point over 3, or you could divide by 1,000, for example, and that would say that 5 amps is the same as 5,000 milliamps. Let's check it out. Yep, 5,000 milliamps is the same as 5 amps. All right, here's another one that happens a lot. A frequency readout shows 7.150 megahertz. What would it be in kilohertz? So now we're converting from megahertz to kilohertz. 7.150 megahertz. All right, and we want to know this answer in kilohertz. Again, we're going by a factor of 1,000, but we're going the other direction now. We're moving the decimal point over 3 places, and we come up with 7150, or 7,150 kilohertz. 7.15 megahertz is the same as 7,150 kilohertz. Let's see if I got it right. I think I did. All right. How many microfarads are 5 million picofarads? Oh my word, Gary, what are you doing? You're making me have a headache. All right. So picofarad is 10 to the minus 12th. We're not going to get into that, but it would be written as, let's see. I have to do it this way. And we said, what did I say? 5 million. So put the 5 there. So it's the same. So we're converting now between picofarads, where to go, and microfarads. So microfarads are millions, tenths, hundreds, thousands, 10,000s, 100,000s, millionth. I don't know if you saw what I did here. This is the number we started out with. 5 million picofarad is the same as 5 microfarad. This is difficult for me to explain even clearly, but it is 5 microfarads, also written with the micro there. All right, another frequency problem here. 21,500 kilohertz is what in megahertz? This should be a little easier. $21,500, what was it, megahertz, right? No, 21,500 kilohertz. What is that in megahertz? So 21,000, this is a comma, or I'll just take it away. 21,500 kilohertz is the same as, going over by 1,000, 21.5 megahertz. You're going to have to play with this a little bit on your own and see if you can factor it out. All right, I think this is the last one. Frequency readout says 5.125 megahertz. What is this in gigahertz? Well, we would just move over by 1,000. I'll move over in the camera here. And the answer is 5.125 gigahertz. That's the same as 5,125 megahertz. And then finally, the frequency and wavelength problems. Remember our pyramid that we talked about. 300 on the top, frequency in megahertz on the left, wavelength in meters there on the right. So we want to know the frequency is 14.2 megahertz. What is the actual wavelength? So I'm going to draw the pyramid out. It's always 300 on the top. And we said the frequency is 14.2 megahertz. Nice that they put it in megahertz. We want to know what the wavelength is. So we would take 300 and divide it by 14.2. And if you take 300 and divide it by 14.2, again, here is our pyramid. The answer is 21.13 meters. Now, experienced amateur radio operators would know that 14.2 megahertz is in the amateur 20-meter band. But our answer here is 21.13. Why don't we call it the 21-meter band? We don't because of convention over time and over history. It's the 20-meter band, and if you look on the color chart, you'll be able to find 14.2 megahertz there. So these indications here are not the actual wavelength of the radio signals. They're approximations. But when you do the formula, you get the actual wavelength of that radio signal. Why is that important? Because wavelength, remember, is how big you build your antenna. If you don't build the antenna properly, then you won't radiate radio frequency energy as efficiently. We'll get a lot more into that as we go along. So, all right, one more problem here. Wavelength is 10 meters. What is the frequency? This is kind of easy. Wavelength is 10 meters. Speed is 300 million meters per second. So 300 divided by 10, the answer is 30 megahertz. All right, you did it. Maybe you didn't do it right with me, but you at least saw it. You participated, and that's great. But here are some actual test questions. This is the first. These are test questions that you would see on your test, very much like we did here. So let's take a look. What is the relationship between wavelength and frequency? And if you think you know the answer, go ahead and unmute if you're in the Zoom classroom. And let me know A, B, C, or D, or better, Alpha, Bravo, Charlie, or Delta. We use the phonetic alphabet. So which one? Alpha, Bravo, Charlie, or Delta?
Bravo.
Okay, I heard Bravo. As the wavelength gets shorter, frequency increases, and that's correct because they are inversely proportional.
Okay.
All right. So what is the formula for converting frequency to approximate wavelength in meters? So we're looking for wavelength.
D.
You hear that? Delta. Wavelength in meters equals 300 divided by the frequency in megahertz. That is correct. That's our pyramid. All right, in addition to frequency, which of the following is used to identify amateur radio bands?
A?
Yes, alpha. The approximate wavelength in meters. Remember, I showed you on the color chart the various band names. They're the approximate wavelength in meters. And what frequency range is referred to as VHF? The FM broadcast band is
Bravo.
Bravo, 30 megahertz to 300 megahertz. Notice some of the units are kilohertz, so don't let that confuse you. This is 30 kilohertz to 300 kilohertz, but no, we're dealing in megahertz here, 30 megahertz to 300 megahertz. These other answers are called distractors. And these are the actual test questions and the actual answers you will see in your test. They just won't be in the same order. So don't memorize A, B, C, or D. That won't do you any good. All right, so what frequency range is referred to as UHF?
D.
Everybody see that? I'm going to give you time to look. She said delta
wait a minute.
300 to
3D.
3,000.
Yep.
Delta 300 to 3,000 megahertz is UHF, or ultra high frequency. So what frequency range is referred to as HF?
Charlie.
Bravo.
It's Charlie. 3 to 30 megahertz. High frequency, then very high frequency, then ultra high frequency. So it's the lowest frequency range, 3 to 30 megahertz. So what is the approximate velocity of a radio wave in free space?
Bravo.
B is in Bravo.
You're a scientist. Remember, we deal in the metric system, so it's 300 million meters per second. So what is the unit of frequency?
Alpha. A.
Think of Heinrich Hertz. And what describes the number of times per second that an alternating current makes a complete cycle?
Delta.
D.
Charlie.
Delta.
Delta, that is the frequency. And okay, here we go. How many milliamperes is 1.5 amperes?
D is in Charlie.
Everybody see that? 1,500 milliamperes is the same as 1.5 amps. Unit conversion. All right, which is equal to 1,500,000 hertz?
C is in Charlie.
Not Charlie.
A.
Everybody see that? A. 1,500 kilohertz is the same as 1,500,000 hertz. We moved over 3 decimal places to get to the kilo position. All right, which is equal to 1 kilovolt?
C is in
Charlie. 1,000 volts.
1 kilobuck
Yeah.
is 1,000 volts is a 1 kilovolt, yes. All right, which is equal to 1 microvolt? Micro is?
One. It's
1 million.
It'd be A.
Yeah, be alpha, 1/1,000,000th of a volt. You got it. So which is equal to 500 milliwatts?
B.
It is the same as a half of a watt, or 0.5 watts. Watts, the unit of power. All right, which is equal to 3,000 milliamps?
D.
It is D is in dog.
Delta.
1,000 milliamps is the same as 1 amp, so 3,000 milliamps is the same as 3 amps. Which is equal to 3.525 megahertz.
C.
Okay, slow down, let other people get an answer, and you're right. It is C, Charlie, 3,525 kilohertz. Okay, which is equal to 1 million picofarads?
B.
It is B, 1 microfarad, 1 microfarad is the same as 1 million picofarads, which is a millionth of a millionth. So which is equal to 2,804 or 28400 kilohertz? You can read it. 28,400 kilohertz. What's the same? What's the equivalent? We're going from kilohertz to megahertz.
C is in Charlie.
Not C.
D.
Going by a
D.
factor of 1,000, so we move over 3 decimal places, and it's 28.4 megahertz. That's okay. This is all new. which is equal to 2,425 megahertz.
A. Alpha.
C.
Not A. So we're
D as
moving.
in Charlie.
Yeah, so we're talking, the unit here is gigahertz, which is a unit bigger than megahertz. So we're again moving by a factor of 1,000, and so it's 2.425 gigahertz. And it'll come to you, you'll learn the relationships between giga, mega, and kilo. It'll become almost automatic. But you're not quite there yet, but that's entirely normal. All right, what does the abbreviation RF mean?
Alpha.
Alpha.
Alpha, yes. Radio frequency signals of all types are called RF. And what is the abbreviation for megahertz, the correct way to write it?
Delta.
Delta.
Delta, capital M, capital H, small z. And what is the abbreviation for kilohertz?
Again, delta.
Yeah, small k, capital H,
Yeah.
small z. And that, ladies and gentlemen, is the end of the section, section 2.1. You did it. Congratulations. And now we're moving on to section 2.2, radio equipment basics. This is my old station at my old QTH. I moved about 3 years ago. And you too will have a ham station. It may not look exactly like this, and it doesn't have to, but we'll talk about that. The basic station layout, though, is really this. It's a transmitter, something to emit a radio frequency signal. There's a receiver, something to receive a radio frequency signal, and some sort of transmit-receive switch, which can switch the feed line and antenna between the receiver and the transmitter. This is a block diagram of an amateur radio station in its most basic form. And early on, back in the 60s, ooh, I lusted over these. These were the Kenwood twins. R for receiver, T for transmitter. Exactly in the way that we just looked at it there. And you actually routed a signal between the two, and the TR switch was, I think, in the transmitter. So when you hit push to talk, the transmitter would be connected to the antenna, and when you released it, then the receiver would have the antenna, and you'd be able to receive. So separate receivers and separate transmitters used to be a thing, but not so much anymore. What we have nowadays are transceivers. It replaces the separate transmitter and receiver and puts all of the functions in one box, the transceiver. And connected to the transceiver are various things that you can use to emit radio frequency energy modes, like Morse code with a Morse code key, or a microphone for voice. Here's a speaker that you can hear what's going on, or headphones. You may need to power your transceiver. A lot of amateur radio transceivers are 12 volt powered, so you need a power supply to convert from 120 volts AC down to 12 volts DC. You may have a power amplifier to increase the output power from the transceiver from 100 watts up to maybe 1,500 watts. And then, of course, a feed line and antenna. So this is a transceiver replacing the separate receiver transmitter that used to be popular. And if you really want to drool, they just discontinued this one, but this was the ICOM model 7851. Ooh, for a guy like me who likes buttons and knobs, oh boy. You know what the price tag was on this guy? $13,000. Oh my God, no. So you don't have to have this, but here is the epitome of the art. This is one of the best transceivers that you could ever come up with. So back to my old ham shack, I was using a flex radio, the 6500 back then, that's right here, and it was controlled by a control panel called the Maestro. And it's a software-defined radio. We'll talk more about that up and coming. But nowadays, this kind of looks like my ham check. I've changed it a little bit, but I have a high frequency or shortwave operating position over here and a VHF UHF operating position over here. And so this is the HF, and here's that Maestro control panel, very similar to what you saw in the other picture, but my radio and amplifier are in a completely different room in the house. And I'll show you that here in a second. And then over on the side here is my VHF UHF position with a Yaesu FT991A radio, also a Kenwood VM71 FM radio for local communications, amplifier and some tuning indicators there. In the storeroom of my garage lives my radio, the Flex 6600 now, that's the current one that I have, and an RF Kit S power amplifier to increase the output up to 1,500 watts, the legal limit for ham radio transmissions in the United States. Why did I configure it in this way? Because in the storeroom, it was easier for me to install 240 volt AC power. So I have a LAN cable or a networking cable that connects the two together. Here also is where all of my antenna lines run out of the house. And I use my little garden shed here and a roof tower, and I have antennas on top of the garden shed. It's not very high up, but I have a K4KIO hex beam, a rotatable directional antenna up about the 30-foot level. That's one of my HF antennas. And then it's hard to take pictures of wires, but I also have some off-center fed dipoles. You can just kind of see the wire there. That's one of them. I have a second one as well. I also have some receive antennas as well. Big changes here at the W4EEY QTH. QTH means location. So we're going to get a new radio. It's on order right now. It's the ICOM IC7760. It's not $13,000, but it's not cheap either. But it will replace the Maestro and the Flex 6600, which will be moving here to the studio. The Flex Maestro will be coming here, and we'll be able to play with it here in the studio, and we'll be able to tune some signals, so you'll be able to see signals and hear them as well. That will be happening in the next few weeks as soon as ICOM ships me my new radio. And so it's exciting, and I think you're going to enjoy it. It'll be the first time we've had a live radio, HF radio, here in the classroom. So it should be kind of interesting. I think you'll find it fascinating. But remember, this too is a ham radio station. When you get your first technician license, you will likely be using a handy-talkie like this Yaesu. Inside this handy-talkie, there is a transmitter, a receiver, a transmit-receive switch, a very short feed line, and then the antenna that's connected to the top. So this is a transceiver, a handy-talkie transceiver. And we talked about some services like GMRS can use radio repeaters. Well, hams have been using radio repeaters for years, and these allow us to transmit from our handy-talkies to a radio repeater that will receive and rebroadcast the signal immediately out on a different frequency at great height. So here you can have on the mountaintop or on a very tall tower. And so from a small walkie-talkie that otherwise might only go a mile or so, you can go 60, 70 miles via a repeater. Hams do this routinely. And repeaters replace that TR switch, remember we talked about before, with something called a duplexer, which is a filter that allows a receiver and a transmitter to be connected to the antenna at exactly the same time. The duplexer is the filter. It filters the signals away from each other. The audio is carried from the receiver over to the transmitter. This is what a radio repeater looks like on the left here, the electronics for it. This is the filter. This is the duplexer. This is the thing that allows both the receiver and transmitter to connect to the antenna at the same time. So that's just a brief overview of some amateur radio stations, layouts, and such. Oh, here's a question. What is a transceiver?
A.
We see that? A transceiver is a device that combines a receiver and a transmitter. And that, ladies and gentlemen, is the end of chapter 2. Let me go ahead and take off my spotlight here. Whoops. Wake up. Where's my... There we go. I lost my cursor. So this is the portion of the program that I like to call class chat. We are done with the formal material. Are there any questions or comments that you might have? Go ahead and unmute and go right ahead.
I have a question.
Yes, please.
I live in like a little rinky-dink apartment, and I was wondering like if there are any sort of like antennas that you can get to like hang from like a window or a curtain rod or something like that, since I can't like formally install one per se.
Yes, absolutely. This is something that can be done. You could use a mobile antenna, for example, that might be designed for a car and hang it off of the balcony. Some people will put up antennas inside of buildings. You have to watch out for the amount of radiation, RF radiation, that might come so close to humans in that. But there are things that can be done, yes. And for an HT, for VHF and UHF, it's no problem whatsoever. Any other questions or comments?
Can you repost if it's convenient the how to pay you?
Yes, indeed. In fact, what I will do is tomorrow you will be getting an email from me, both on our Zoom mailing list and our YouTube mailing list. And it's also in the description box on YouTube. If you look there, there's a Dropbox link. I will be posting this presentation as a PDF file. So you'll be able to look at it in there. You'll be able to catch it from there. And, no hurry, no rush on getting money to me, but donation would be helpful. So you'll have all of that,
Yeah.
plus a lot of other stuff, an audio file of the class, another video file of the class, a transcription. We give you a lot of stuff. We give you more stuff than you need. Plus, something we're going to give you is the Right Answers Study Guide, which are just the test questions from this chapter with just the right answer, which helps some people to associate question and answer. Any other questions or comments? Yes, go ahead, Julie.
I have a question. Do you know of any workbooks that we could practice the mathematics?
So there are some YouTube channels and some YouTube videos that you might find helpful. There are other study materials available, other books and whatnot. I'll try to provide you in an email links to those so you can check them out.
Okay, thank you.
You bet. Mark, go ahead. You had your hand up? Oh.
I got I borrowed the actual book from the library, but I was also going through the hamstudy.org book.
Yeah.
Now, does that have the same material in it as so like if I have to return the actual book that I borrowed from the library, does it have the same material in it?
It covers the same questions and the same answers. As long as it's the current question pool, the current series, then it will be the same questions, the same answers. How they present the information, there are books from Ham Study, there are books from Gordon West, there's the American Radio Relay League. They're all covering the same material, but from just a different perspective.
Okay.
Question.
Yes.
Could you go back? I'm still trying to understand. I know for a repeater in the world of electronics has to do, I think it's with amplifying a signal, right?
Well,
in this case,
a repeater, that would be an amplifier. If it's amplifying a signal, it's an amplifier. A repeater is receiving a signal on one frequency and retransmitting it on a different frequency. So
you had a picture in the slide, one of your slides before the conceptual diagram in the ARRL book.
Yeah.
Where you said that a lot of times they'll put it high on a hill.
Yes.
Can you just kind of talk about that a little more? I'm trying to conceptualize what it's actually doing.
Sure. Okay. So here's the slide. Bruce can probably put it up here in just a second.
That's it.
Yeah.
Yep.
And here in the upstate of South Carolina, for example, we have a repeater, 2-meter repeater on 146.610 megahertz. It's known as the Caesar's Head repeater because it's located on a TV antenna tower on top of Caesar's Head Mountain, part of the the Blue Ridge Mountains, and so it's at an elevation of 3,500 feet above sea level. Whoa! And so with a little walkie-talkie here in the studio. Well, probably in the studio, maybe not, but outside, I can bring up that repeater and I can talk almost all the way to Charlotte, North Carolina, almost all the way to Columbia, South Carolina, and into North Georgia. That's what we call a wide area repeater. And so that allows you to talk to mobile units or other handy talkies or base station radios all over the region. The other thing is that many repeaters, and we'll talk more about this in future classes, are linked. So they're linked to the internet. They're linked to some systems called EchoLink or Internet Relay Linking Project that allow you to get on one repeater in one city and come out on another repeater in a different city. So you might have a friend in Dallas, Texas, for example, and if you're using a linked repeater, there's a way for you to go into the repeater here locally and come out there. There's also digital modes now, and I hope to be able to demonstrate. We just have a new Yaesu Fusion digital repeater here in the upstate of South Carolina, and it allows you to select where you want to come out right on the radio, and in so doing, you can actually talk internationally. It links via the internet to other Yaesu Fusion repeaters in the UK, for example, or Japan, or a lot of different places. So even with a handy talkie, we talk about its basic function, but there are some very sophisticated functions that can go along as well, so you can talk at great distance. I probably...
Question?
Okay.
Yes, go ahead.
I have one of those handy dandies, and I'm not sure if my question is applicable to everybody in the class because I think people are from other places. I'm also from the upstate of South Carolina, and every night I listen at 8:30, and people do radio checks.
Okay.
My question is, are they talking on a ham radio frequency, or are they talking on a shortwave or HF? I'm a little confused about that part.
So if you're listening on the little radio that I just saw there, are you in Anderson, South Carolina?
Yes, sir.
Okay, so
Yes, sir.
me too. I'm in Pendleton, so we're very close.
Me too.
Yeah, and so yes, the Anderson group has their net, their nightly net. That's what it's called at 8:30, and they're talking on VHF frequencies, amateur radio frequencies, into a repeater that is then being rebroadcast on the repeater output frequency, which is what you're hearing. And when you get your license and call sign, you'll be able to participate by transmitting into the repeater and coming out, and they'll be able to hear you, and you'll be able to participate with that. In Greenville, just another county over, they have a nightly net on the Caesar's Head repeater at 9 o'clock, which is why I asked if you were here in Anderson, because I know that's at 8:30. Did that answer the question?
Yes, sir. I was wanting just clarification. I know this picks up, quote, ham radio, and we're talking about the high frequency and the VHF and UHF, and I don't have it all clear in my head, and I just wondered if that conversation that y'all are doing, with which frequency that was taking place on. Is it on a ham radio frequency versus...
It's in the
shortwave?
2-meter band, so it's going to be on the color chart. You'll find the 2-meter band, and that it's a frequency there. I don't remember off the top of my head what the Anderson repeater frequencies are, and so that's where they're transmitting. It's 146 megahertz or thereabouts in that range. VHF, it's a VHF. Also in Anderson, they have UHF repeaters as well, and it's possible they have them cross-linked for the net so that you could come in on UHF and come out on VHF. I'm not sure about that. Yep, it's either VHF or UHF is what you're hearing.
Thank you.
You bet. Very high frequency or ultra high frequency.
So that's how you get the distance then, is you're converting from one band to another.
Well,
potentially.
so different radio frequencies propagate differently. VHF and UHF are mostly line of sight. We're going to talk more about that in upcoming classes, but great questions. And so, line of sight. So if you could see the tower on Caesar's Head Mountain, for example, if you have really great eyesight, then you can probably get the radio signal there. Now, shortwave or high frequency radio uses a different technique where you actually transmit the signal up to the ionosphere above the Earth, and it's refracted
Right,
back
okay.
down, and that can go thousands and thousands of miles away via the skywave
Got it.
transmission.
Yep,
More to come. We're going to talk about all of that. It's coming.
makes sense. Okay, thanks.
All right, well, let's close it out there. I appreciate you. As I mentioned, 73 is a telegraphic shortcut term for best regards. So we close it out every night with 73, and we will see you next week for Chapter 3.
I heard we're going to acquire Garyland.
Trump's working on it, I think. Yeah.
Have a good one.
73.
73.
73, thank you.
Seven threes.